Okay, let's get started. Last week we looked at the overview of controller operation. So you see here we have assembly code like this, right? So this is our code. And when you have assembly code, you run the assembler with this code. And assembler converts this assembly code to the binary. For example, like this. When you see the binary code and assembly code, you will see a one-to-one mapping. This line, this instruction is mapped to this binary. That's what assembler does. What the assembler do is that parse this line, parse of each instruction, and map it into the binary. Simply, that's what assembler does. So you see that this binary corresponds to the first instruction. Second instruction corresponds to these two bytes, right? And this binary file is now downloaded into the code memory. And later, when you power up, when you boot up your machine, the microprocessor will fetch from the memory, fetch instruction by instruction, line by line, fetch it, and then decode, execute, and write it back. Okay? So that's the pipeline procedure happening inside the microprocessor. So we learned the syntax of assembly language. If every line of instruction, every line of assembly language has this format. First, you have label. Sometimes you have it, or you may or may not have it. And you have instruction. If you need, you can put a comments followed by semicolon. Each instruction here, right? This instruction right here has two parts. First part is called the OP code, or sometimes we call this a mnemonic. Second is operand. OP code followed by operand, sometimes one or multiple operands. Example is that move. Move is one of the OP code. Okay, and move is from copy a data from one place to another, right? So you basically copy value from source to destination. So therefore, you have to have two operands in case of move OP code. So here are example. Move A, what is this? Pound or hash. Okay, so we call this pound. Generally in US, we call this pound. In UK or some of the European countries, they call the hash. Okay, it's basically the same thing. So pound 01H, that's immediate value. So you put this value into A. Okay, that's what this instruction does. And also you have other type of move. In this case, it's the direct addressing. This is indirect addressing, right? So what you need to understand is that what happened to the registers and also the memory when you run this kind of assembly. Okay? You need to make sure that you understand what happened. When you execute every line of instruction, you need to make sure that what happened to the registers. Okay? That is very important. We learned assembly addressing modes. There are 5 different modes. First one was immediate addressing. Simply, the immediate addressing is that you copy the immediate value to the register. For example, in this case, you move 01H. 01 is a value, and this value, put that into A, right? Copy into A. On the second line, 31H, that value copy into R0. So that's immediate addressing. Okay? Simple as that. Register addressing mode is that you copy a value from one register to another between the A and R0 to R7. Okay? So you want to copy the same value to from these registers to A or vice versa. Okay? If you want to do that, then you can use this kind of register addressing mode. Direct addressing mode, this is probably the most popular way of using move instruction. If you have no hash or no pound or no at, okay, you just have just value, 04H. In that case, what that means is that 04H is the address. Okay, it's an internal address in this case because this is just a byte, 8-bit. Okay, this is internal address. So when you have this instruction, what that means is that you are not copying this value into A, right? Because this is not a value. This is an address. what happens is you go to that address. Okay, this address may have a certain value. Okay, copy that value into A. Okay, use this one as address. That's direct addressing mode. Similarly here, in this case, you copy the value in A into address 34. Okay, 34H. 34H is the address. In this case, destination address. In direct addressing mode, in this case, you have at. Right here, as you see here, at, right? So look at the example here. The first line, first instruction is immediate addressing. So you have a value 30H. Copy this value into R0. So once you do this, right, the R0 register has the value 30H. And now on the second line, second instruction, you execute indirect addressing mode. Then what happens is this 04H, which is address, right? You have some value in the 04H. That value now is copied to where? 30H. Okay, 30H is going to be destination address. So that value, so simply speaking, right, what happened within these two lines is that the value in the 04H, that is copied to 30H. Okay, that's what simply happens. Remember that you should be able to read these codes. Okay, you should be able to read these codes, and you need to make sure that you understand what happened to the registers for every single line. You execute this line, then something happens, right? In this case, R1 now has this value. Okay? Second line, when you execute second line, what happened? 55H goes to A. Okay? So every single line of instruction, you need to understand what happens to the registers. Okay? What is the best way to do it? Use your emulator, simulator, okay, in your PC. And write down your assembly code and just run line by line and see what happened to the register values, right? That's the best way to learn this one. And possibly midterm or sometime maybe quiz, I'll probably give you some blank, maybe here somewhere. Or maybe I'll give you register A, R0, something like that. And when you run this code, you need to write at the output. When you run all these things, then eventually what's going to be the value after you run all this code. Okay? Some of those things I'll give you. I'll put that into the midterm and also the quiz. Okay? Why do we have this label, especially for this line? Because this particular line is referred by that line, that instruction, right? This instruction is a jump instruction. So when you want to jump back or jump forward, then you need to specify where to jump. To do that, you have to have a label, okay? So that way, this jump basically goes to our repeat, and repeat is right here, right? So that's why we have a label in this particular line. There's an index addressing mode. In this case, the difference is that you use this particular value as an index. Okay? This one is a base address, and this one is index. So how you use it is that this base address does not change. The value in here is the same, but only this one, right? This value, the value in here is actually incremented. By doing that, since you add it all together, base address plus some value, and this value is incremented, therefore this address is now incremented. Okay? That's the purpose of using this index addressing mode. I think this is not that popular. I think when you write assembly code, you probably not going to use this one. The popular one is direct addressing, indirect addressing, immediate addressing, those things. Okay, today we're going to look at the assembly instructions. Okay? First of all, we need to learn what is instruction and directives. We know the instructions. Like instruction is like a move or add or something like those. Okay, we'll look at it in the next slides. What are directives? What is directive? In C language, you also have directive, right? What is directive? Okay, let's see. This is an example of C language. You have a C language, your own C language. But when you make a C language, like this one, right? For example, this is my program.c. You have something more here, something on top here. What do you have? Huh? For example, like, right? You have include, maybe standard input-output header file, something like this, right? Or sometimes here you may have define A100, something like this, right? So those things are directives. These are not C code, right? Your actual C code is here inside the function. These are not inside the function. Then what is it? That's not C code, right? I mean, that's not a part of your execution. Then why do you need this? Okay, so here's the thing. The code inside your function is compiled. So this is your C code, and you're going to run the compiler with this, right? So compiler will look at this one and convert each of these lines inside the function into a binary. Okay? So all of these things will be execution. This will be your code. But these parts, directives, the compiler will look at directives, and they are not going to convert it to the binary. Those will not be binary. Then why do we need this? First of all, why do you need this? Include. Why do you need this? Does anyone know?
Because some functions are included in
Okay. Let's say you don't have this, then what happens? If you don't want to have this, right, then you have to make every single function by yourself. But standard input-output header file already have some of the functions available for you. That's already provided by the library. Okay? So for some of the basic input-output functions, you don't have to make. Someone already made it for you, right? Okay, as a library. And also they tell you that, okay, this is a function template. I made the function already. I have already function. And this is the function template, and you can use function this way. Here's the input, here's the output, and this is function name. You know, you can use this way. Okay? So already the functions are already defined, right? Defined somewhere. So in this, your program, what you need to do is that you basically include those definitions, those function definitions, and just use it. For example, right? Printf. You always use printf. This is not your function. You didn't make it, right? Someone else make it, right? So where is this function? So some library. And someone make this function and define this function as a template here in this header file, right? So by simply include it, you can just use it. Because this is already defined inside this header file, you can just use it. That's not your function. You didn't make it, but you can use it. So that's the purpose. So this particular line will not become binary. This line is not going to be binary. This is not your code, right? This is just simply a definition and tells the compiler that, okay, this kind of function, you can find it here. Only that's the message. What about this one? Sometimes you have another directive called the define, hash define A100. What is this? This one is different from this one, right? You may have this one somewhere here inside your code. Maybe inside your code you have integer A equal to 100. Maybe you have this line, right? This one and this one is different. This line is your code. So this will be compiled and become binary. This one, it's not, right? What is this then? Yeah, that's a global definition, but why do you need this? Simply the reason is that when you have this defined, then inside your code, you can use A. For example, A plus 5 equals B, something like this, right? In that case, the compiler will look at this one, this line, and finds out that, okay, A, capital A is actually 100. So the compiler will replace this one into 100. That's what compiler does, right? So this particular line is not your code, okay? This just helps the compiler, okay, to find out what is actually the value of this capital A. Do you see what I'm saying? These are actual code. This is not actual code, okay? This one, these directives basically helps the compiler how to find, where to find the function, and what is actual value of A, and those things, right? Same here in assembly. We have directives in assembly language. For example, like this, right? Here are examples. CSEG, what is a CSEG? Code segment. Code segment, okay? Which means that these are the segments, memory segments or address segments for your code. Okay, so your code will be here in this segment. That's what they mean, CSEG. But your code is right here to here, but this is the base address, the lowest address of your code. So your code, when you look at this line, then what that means is your code will be in 1000H, 1001, 1002, 3, and something like this, right? Your code will be here. That's what this means. This itself, this line is not instruction. Okay? These are directives.
And is it similar to program counter?
No. Program counter, okay, this one just defines the lower boundary of your code. Okay? Maybe initially when you power up, okay? When you power up, then maybe this value is same as PC, program counter. But when you execute line by line, this is the baseline, base address of your code. And then next code will be 1002 or something, right? 1004, 1008, something like this, right? The program counter will increase. But this one is same. I mean, this one just defines, okay, here is my boundary. That's it. Okay? So this is one example of directive. And this one is another way. SP, data, 0.0x81. This is same as 81H. Okay, hex. SP, stack pointer. Okay. Data 81. So which means that what is this one? This one actually, this line is same as that defined in C language. In C language, right, you define A 100. Same here. SP, it's like a define SP this value. It's the same thing. This is assembly way of define. Again, this is directive. This is definitely different from SP equal to 0.x81. That's not the case, right? This is not instruction. Look at third line. Third line, fourth, the last line, these three lines are same, basically. What it is that limit, again, this is just same as define. I define the limit 2000. Okay? EQU, equals, right? Limit equals 2000. Something like this. Okay? Green LED equals P 1.6. Count equals R5. Okay? Just equals. But all of these lines are not instruction. So the compiler, the assembler in this case, assembler will not convert each of line into binary. Assembler will simply look at it and then use this value if necessary. So for example, right, I have this line. And later in my code, in my actual assembly code, I will use limit. For example, I do like add limit A or something like A limit, something like this, right? I do it later. For example, I do like add A limit, something like this, right? In my assembly code. When I do this, right, then the assembly will look at that particular directives and find out what is actual value of limit and replace this into 2000. So compiler, the assembler will do it. Then now the question is, why not just I use just 2000 here? Why do I want to use limit here? I can just use 2000 here in the code, right? You can do it. But in that case, you do hard coding. Hard coding is a very bad practice when you write a code, right? It's always a good practice, use a variable. Same here, right? You don't have to have define a 100. In fact, you can actually have 100 in your code, but that's a very bad way. This is hard coding. You don't want to do it. Okay? Same reason here. You have equal and define a variable. In this case, it's a constant. It's not a variable, actually. It's a constant. You define a constant like this. And later in your code, you don't want to use this number. You use this name, right? That's a more readable code. Okay? Readability is very important when you write a code. So that's one of the reasons. P 1.6. P1 is what? Port 1. Dot 6 means bit 6. Okay? Okay. For instruction, we have many instructions. In 8051, we have a lot of instructions. So we have 8 bits for instruction. How many bits? How many value can you have with 8 bits? 2 to the 8, which is 256, and 256 minus 1. So that's going to be 255. We have a 255 different instruction, different binary. Okay, binary. Instruction, maybe it's the same. For example, move instruction has a mapping to multiple binaries. Okay, we'll see that later. But anyway, we can have a 255 different binary. There are 5 different categories of instructions. First one is data transfer, arithmetic, logic, Boolean, branching, and we'll look at one by one. There are also other type, like stack instructions. We already learned the push and pop, right? And push and pop, you have only one operand, byte. Okay? And what the push does is that stack is a special memory such that there is only the bottom on the stack. That's pointed by stack pointer. Okay? Stack pointer will tell you where is my bottom of stack. Okay? That stack is like a box, right? So the bottom of box, okay, that is indicated by stack pointer, right? And now if you push one thing into the stack, so for example, I put a book, one book, push it into my box, right? Then your stack pointer is increased because the bottom, the floor is now increased because I put one book here, right? Right? So every time you push, the stack pointer will be incremented. And every time you pop something out, the stack pointer will be decreased. Okay? One thing is that if you want to pop some value, but that value is in somewhere on the bottom here, then you cannot just pop that one. What you have to do is that you have to pop all of those things first, right? All of the top value you have to put it. You have to pop it first, and then you reach your own value and pop it. So that's called the LIFO, last input, first output, or first input, last output. Right? But these two instructions are stack manipulation instructions. For data transfer instructions, generally we have move. Move is data transfer. You are copying value from one place to another. We have 6 basic types. All of these are move instructions. Only difference is that you're moving byte to A, the value in accumulator to byte to some registers. Rn means R0 to R7. Okay, n means any numbers. So you can copy the value into R registers, or byte to direct address. This can be address. Byte to indirect address. Okay, or in this case it's a data 16 because we have a 16-bit data. In this case, all it's 8-bit because we are right now from here to here we are assuming that we are copying the value from internal register to the internal memory, or internal memory to register. So all of those source and destination, all of them are internal register. But sometimes if you need, then you want to copy the value from internal to external memory or external to internal. In that case, external memory, you will have 16-bit address. Remember that we have 16-bit address, 64K address spacing. That's the external memory. So if that's the case, then we have a 16-bit data. In this case, the 16-bit data is actually address. Put that into DPTR. DPTR is a data pointer. Okay? This is one of the registers. This register particularly is 16-bit registers, right? The value inside this register is actually address. Okay? So sometimes if we need, then you can do it this way. Okay? So we have different types. So it looks like all of them are move instructions, but these are different types, right? So when you run the assembler with this code, the assembler will look at what type it is, right? When you have a move instruction, then your move instruction will be one of these types, right? And the assembler will look at, okay, what your instruction is corresponds to, which type you have. And based on the type, the assembler will convert your code into the different binary. These are all same move instruction, but still this one, when this one becomes binary, this one, for example, this one becomes like a 7F, this one 7E, maybe this one 6F, something like this, right? That's what I'm saying. How you map it, how you map assembly with the binary, that one we'll look at it maybe next week or so. Okay? But anyway, simply the assembler will do a mapping between the assembly code and the binary. Simply mapping. You can actually do it by yourself. That was actually one of the midterm last year. Okay? So we can do it actually. Okay? But remember, not all the move instruction is the same binary. That's what I'm saying, okay? Different type of move, you have a different binary mapping. You have different mapping. Okay? And how many binary type we have? 255, 255. That's what I said here, right? We have 8-bit instructions, right? So we have, and except A5, we have a 255 binary from 00 to FF, right? 00, 01, 02, all the way to FF. We have all 255 different binary, okay? And each of these types will have a different mapping. Another data transfer instruction is exchange instruction. Simply, what exchange does is exchange the value. Here, XCH, A byte. Then what happened? You basically swap the value. Okay? Switch, exchange the value. The value inside here goes to here. The value in here goes to there. Something like this, exchange. And exchange D means that, again, you exchange, but you are exchanging only low nibble. What is nibble? Nibble. Have you heard the nibble? Maybe these days, you probably don't have a chance to hear the nibble. You know byte, right? Byte. Byte is 8-bit. What is 16 bits? Generally, 16 bits, we call this half word. Half word. 32 bits word, right? Generally, that's how you call it, right? Actually, it depends on the system, but I'm talking about generally. Generally, word is 32 bits. Half word 16. Byte 8-bit. And generally nibble 4-bit. It's not always this case. Not always, but generally it's like this. Okay? These days nobody cares 4 bits, right? We are living in 32 bits these days. No one cares about 4 bits. But think about it. This one was like a 30, 40 years ago. You know, even 4 bits was very important at that time. So that's probably why they have these instructions. No one uses this instruction anymore, right? But anyway, nibble is like this, 4 bits. There are arithmetic instructions. For example, add, addition, add C. C means carry. Okay? So this is simply addition of these two. And add C means you'd add with carry. I'll tell you what it means. Okay? Add C. Sub is subtract. Okay? Subtraction. But you have addition of B. Subtraction with borrow. What is borrow? Okay, I'll tell you in the next slide. Increment. +1 every time. Every time you do +1. Okay, increment. Of course, you have decrement. -1. Every time you run, -1, -1. That's decrement. Increment, you can actually increment the value in A, or you can increment the byte. You can the value in the byte. Byte in here is that actually the address. Okay, you go there you go to that address, then you will find the byte. That byte you can increment, and also the pointer you can increment. Decrement also, you have, you know, the value in here you can decrement. You can do -1. There's an instruction called multiplication. Okay, multiplication, and also division. And the last one is decimal adjust. I think this one is not that popular again. This is a little bit confused. I don't know. Maybe someone use it, but I think this is not that popular, not important. But anyway, let's find out. So let's find out one by one. Here's the add instruction. We know add instruction. Let's see add. We have add accumulator, comma, byte. In that case, you are basically adding these two, and the result goes back to A. Okay? Always that's the case. Which one is source? This is source. Think about move. Okay? Move instruction. The second one is always a source. First one is always the destination. Same here. Add. This is going to be the destination. This is like a source. So you are adding these two, and the result goes to the destination. Okay? So therefore, you do add like this, then this one goes to here. I think this is wrong. Okay, maybe I want to change it. So A should be here. Okay? You just switch these two. I think this is typo. Okay, then now let's look at add C. Okay? Only difference between this add and add C is that this add C is adding these two, A plus byte, and you also add carry. That's the difference. You have C, right? C means carry. So what does that mean? This one we know that, right? You basically add the two different values. The result goes to A. Then what is this? What is carry? Where is carry? Carry is right here in the program status word. PSW, this is one of the registers, right? It's very important to understand this one. Remember the overflow, carry, those things. when those flag is up, okay? The condition, that's important. So carry is right here in the carry flag, okay? So this is just 1 bit. Carry is going to be either 0 or 1. So you're adding it. So if the carry is 0, okay, then this one is the same. If the carry is 0, then this one becomes same. The output will be the same. But if the carry equal to 1, then the output is not the same. So let's see. Let's see example. Let's see our A has this value. Not this one. Let's say our A has this value. And we have R0. Let's say our R0 has this value. And we want to do add like this. What happened? What's the result? Once you do this, right? The result becomes this, right? Simply addition of these two. Okay? You add these two, that goes back to A. Let's say your program status word, initially you have carry becomes 0, overflow becomes 0, and also auxiliary carry, those things. But let's say we are only worried about carry right now. So let's say carry was 0. And when you do addition, what happened to carry?
Zero.
It's still 0. No change, right? That's what happened. This is simply add. Now, let's say we want to have different value. Let's say maybe we have this one or something like this, right? In that case, you add these two values. Then the output becomes 0, 0, 1, 1. Let's make it this way. 1, 1, 0, 0. Okay, you'll have this value in accumulator, right? When you add these two, in fact, carry flag is up, okay? Because our addition, the output becomes 9 bits, right? Because these two are too big, too large value. So when you add these two, simply add it, then the output becomes 9 bits, okay? It has to be 1 here also, 9 bits. But since our accumulator is just 8 bits, this first one goes away, but instead you have a carry flag, okay? So this is going to be the result when you do add, okay? Right? So now later, right here, later, let's say we want to do add C, A. Let's say I want to do this. Maybe first, let's say I just do add again. Add A01. In this case, I'm going to add the value in A plus 1. Okay? Then the result becomes simply this one, become plus 1, right? Simply that's the case. But now, let's say I do this way, add C. Then what's the result? The result is going to be this one plus this one plus this one. Okay? Because I have add C. You also add carry. What's the outcome? That's the outcome. Okay? This one plus this one plus this one. That's add C. Why do you want to do this? Think about it. Why? Any use case? Here's the thing. Let's see. Let's say I want to let's say I want to add two big numbers. Okay? Two big numbers. In this case, big number means let's say I want to add 75 plus 129. 120. Yeah. Let's say I want to add these things. Okay? In this case, when you do addition, it becomes 195. But in our case, if you use 2's complement, then simply this value becomes too big. Right? If you use 2's complement. So therefore, what happens is this value now becomes minus some value. Okay? And then what flag do you have? In this case, overflow. Yeah, you have overflow flag up. Okay? In this case. But now, let's say I want to do this addition. I want to add two big, really big number. How can you do this? Okay, let's do it this way. Simply, let's say I want to do this addition. How can you do it? By the way, this was one of the midterm. How you can do this? We have 8-bit microprocessor. Okay, but this one is 16 bits value. Okay, large value. We know how to do addition of this because put this value into A, put this value into maybe in some R0, and you run this way. Okay, you basically do add A plus A R0, then you can do addition. Then how can you do this addition with the 8-bit microprocessor? The value is 16 bits. How can you do it?
What if 21 is?
Hmm? 21 will be what?
This is just my guess.
Actually, that's good approach. So what happened is that this value, 2175, you divide this, okay, and you do this addition first. In that case, you do the same way, right? When you do this, right, then sometimes if these values are too big, in this case, it's not too big, so it's okay, but let me change this value. If you have this value, then this case, you have carry. You may have carry, right? Because you add these two values, it's too big. So you have some value out here, and you have a carry. And this carry, you're going to add it with this. Because now you have carry, then it goes to this way, right? So you're going to add these two, carry with these two by add C. So this one you do add, this one you do add C. Okay? And then put these two values together with the 16 bits. That's going to be the outcome. So that's how you do 16-bit address, 16-bit addition. So you need this kind of operation to do that, add C. Simply, only difference is that you are going to add these two with add, but add C, you are also adding with a carry. And another thing is that you need to understand these things when carry flag is up, when overflow flag is up. Okay? And also auxiliary carry if you want. Okay? This is exactly condition. Remember, microprocessor is a very simple hardware. Okay? Microprocessor doesn't know anything. If this is a negative value, positive value, or this is a value 7, value 9, microprocessor doesn't know anything about that. Microprocessor only knows this condition. When you do addition, if the result is greater than this value, then carry is up. Simple, like this. Okay? If there is a carry out of bit 6 and 7, but not both, then overflow flag is up. What does that mean? Okay, do you understand what this means? If there is a carry out of bit 6 or 7, but not both. Okay, I'll show you in the next slide what that means. First of all, this is an example. We have add instruction like this. So first of all, let's put 3FH as a value into A, and let's do addition. And in that case, you add this value and this value, right? Okay, you add these two, like this, for example. We have a 3F, this one, D3 here. When you do this addition, this is going to be the output. Okay, this will be the value remaining in A. Your A will have this value. That's wrong, right? This is pretty small. We are adding pretty big values, but the result in A, the value remaining in A is actually smaller, because in that case we have to check carry. In that case, the carry is up, right? Because the result becomes 9 bits. And not only that, you see that we have a 1 here, right? Which means auxiliary carry is also up. Okay? These are conditions. So every time you do this instruction, add instruction, subtract, and those kind of arithmetic instruction, PSW value will be changed. Every time you add, subtract, or any kind of arithmetic operation, PSW value will be changed every time. Okay? So this is one example. Here is the picture describing overflow. Look at the example here. Here, let's do addition. Let's add 127 plus 115. These two are pretty big numbers, and let's add these two. Now then you see that both values you have a 0, 0 on the first bit. On the MSB, most significant bit, you have a 0, 0. But the result, you have 1 here. That's a carry from bit 7. Okay? Actually, bit 6. Yeah, bit 6. 0, 1, 2, 3, 4, 5, 6. Bit 6. So from bit 6 to bit 7. Okay, that's what they say a carry. Typically, right, when we say carry, it's a carry out of this, the most significant bit, right? When you have a 9 bits, 9th bit, that's a carry. That's true. I mean, that's true. But in this case, whenever you have a carry from certain bit position to another bit position, we can also say carry. Okay? That's what I say carry here. That's what it's saying. If there is a carry out of bit 6 or bit 7, that means you have a carry from bit 6, you have a carry from bit 6, like this, or you have a carry from this to that. That's what they mean, okay? Carry out of bit 6 or out of bit 7, but not both. So that's what we see here. So this is a conditional overflow. You have 0, 0, but the output you have 1 for MSB. Okay, this is a conditional overflow. Look at this one. You have a 1, 1 for MSBs for both values, but output 0. Okay? What is this condition? This condition is a carry from bit 7. Think about it. When you add these two, right? Then 1, 1. So you have a 1 here, right? 9th bit, you have a 1. So this is definitely a condition you have a carry flag. Okay? Because the result becomes 9 bits. You have a carry flag. Do you understand what I'm saying? I'm talking about the carry flag in the PSW. Okay? This carry flag. I'm talking about this carry flag. Okay? This carry. In this case, if you do this addition, you will have a carry flag. Also, overflow flag is up. So carry flag is up, overflow is also up. Okay? Carry flag is up because when you add these two, the result becomes 9 bits. And overflow is up because you have a 1, 1 and you have a carry from this bit, that becomes 0. So you have overflow. So let's look at this example. In this example, right, you have a 0 and 1. You have two values. One value you have 0 in MSB. The other value you have 1 in MSB. And when you add these two, that becomes a 0. In this particular case, there was no carry from bit 6 or bit 7. In this case, right, when you have add these two, this is a bit position 6. Okay, this is bit 6, right? In bit position 6, you have a 1, 1, so therefore you have carry. Okay? But in bit 7 position, you have a 0, 0, so there's no carry. So only the bit 6 has a carry. So you have overflow. In this case, you have a 1, 1 here in bit 7, bit position 7, you have a carry. But look at the bit 6. You have a 0, 1, so there's no carry from the bit 6. So only the bit 7 has a carry, so you have 1.
What if 6 and 7?
That's this case. That's actually other case. Actually, this case actually is that you have no carry from bit 7, no carry for bit 6. So you have an overflow 0. But as he asked, his question is, what if both bit 7 and bit 6 has a carry? Okay, that's his question, right? Think about here. Here is 1. In that case, you have a 1, 1, you have a carry. You have a 1, 1 here in the bit position 7, you also have a carry. In both bit 6 and 7, you have a carry. Then, look at here. If the overflow is 1, if there is a carry from bit 6, or you have a carry from bit 7, but not both. If you have carry from both bit 6 and 7, then overflow is 0. Okay, that's what this means. Why is that? Okay, first of all, this is what hardware understands. Microprocessor simply check this condition. Okay, microprocessor doesn't know what it means. Just simply check this. And then if this is the condition, then overflow 1. Okay? But we want to understand why. So let's think about it, why. Simple interpretation is that, let's look at this case. In this case, you have a carry from bit position 6, but no carry from bit position 7, so you have an overflow 1. But look at this one, what this means. This one is a pretty large positive value. This is also large positive value. When you add these two, the result becomes big value, big positive value, but actually this value is actually negative value. Look at this one. This is actually negative value. When you think about a 2's complement, okay? By the way, reading this one as a 2's complement, or reading this value, or unsigned or signed, this is all by us, right? We do it. Microprocessor doesn't know anything. When we look at this one as a signed value, signed integer, then now we know that this is positive value, but these are two big values. So when you add these two, this is actually larger than 128. 128 is the largest value in 2's complement. The minimum value is minus 128. So if you have a large value larger than 127, then the value goes wraps up like this and becomes negative. So this value actually is a negative value. Okay? When you read this one in the 2's complement, then this value actually is negative. This value, you know what I'm saying? If you read this value with unsigned, then this value is 242. But if you read this one as a signed, using 2's complement, then this is negative value. And this condition, overflow becomes 1, basically gives you a hint. Okay, if you read this one as a signed, then please be careful, because this value is not this one. If you read this one as a signed, then this one is negative. Okay, so please be careful. That's the condition. Raising the flag, please be careful. Okay?
So read the values whether it's sign value or unsigned value. That's
If that's up to you. That's up to you. Okay? If you want to read this one as unsigned, in that case you don't have to worry about this. You can ignore. Okay? No problem. But if you want to read this one as signed, okay, then you have to be careful. Okay? You always have to check the overflow, because this condition happens and the value here, right here, actually is negative. Okay? So same here actually. Both one are negative values. And when you add these two negative values, the output is supposed to be another big negative value, but actually becomes positive. Okay? Same way, negative plus another negative, it becomes positive value. So it's the same condition. But now look at this one. One is positive and the other one is negative. So when you add these two, somehow they cancel out and the value is within our range. So no problem. And now think about that you have a carry from both of them. In that case, you have the same situation. Okay? You don't have a wrap up. In this case and in this case, what happened is you have a positive value. Let's say here is 128, the bottom 127, and bottom is minus 128. You have some positive value plus another positive value. When you add these two, the result becomes too big, so therefore you wrap it and becomes negative. That's this condition. Okay? Second is that negative plus negative, it goes back, becomes positive. So those are the conditions you have overflow. And this overflow is giving you a warning. Okay? Warning. Please, be careful. This condition may happen. And when you read this one as assigned, then you have to worry about the overflow condition. Remember, the overflow and carry flag is completely independent. Okay? In certain cases, for example, in this case, you have overflow up and carry flag up. Okay? And also maybe, not in this case, but maybe other cases, auxiliary carry also is up sometimes. Let's look at subtract instruction. We have a subtract instruction. Subtraction is like a minus some value, and the result becomes a, goes back to a. Similar to add, right? A minus something becomes a. In case of add instruction, you have add and add C. But in this case, subtract, you have no, just sub and sub B. Okay? We only have a sub B. Why? Because in subtraction, you always have to think about the carry. Always. Then this is called the borrowing. B, borrowing. So what is borrowing? What is borrowing? Going back to your elementary student, maybe you have a cousin and ask what that means. So let's say you have A and let's say R0, and you have a value 100. We have a value 30. Let's make a small number, like a 25 sub B A R0. Then the result you have in A is going to be 15. Okay? A minus B. That goes back to A. What can happen is that sometimes you have this condition. 20 minus 25. This is not defined. Okay? You cannot define this. Right? Okay, in this case, you have to have a borrow. Okay? That's a borrow, right? Carry is like a 9th bit. You have, let's say you have 8 bits. Okay? You are adding another 8 bits. then the result becomes 9-bit. That's carry. Let's say we want to do subtraction like this. Subtraction. Let's say this is 20, this is 25. This is actually smaller. In that case, how can you do subtraction? You first have to borrow, right? You have to borrow, carry. So in this case, you have a carry flag also. When you do this kind of calculation, the carry flag is up. When you do when you do the addition, right? The result becomes 9 bits. You have a carry flag up. In subtraction, whenever you do this calculation, carry flag is up. Okay? If you do this calculation, carry flag is still 0. No problem. Nothing to do with carry. But you have this subtraction, carry flag is up. Because you have to borrow it, right? Whenever you borrow, carry flag is up. You can look at these examples. Okay? Let's look at the example here. We have a value 31H, immediate value, and copy that into A. Okay? A now has 31H. Sub B, A, 03H. So in this case, you subtract the value in A minus 03. So that's what happened here, right? Here. So 31H minus 03H. So the result becomes 2EH. That now is in A. A has this value. On the next line, we want to do another subtraction, but in this case, the value is too big. A only has a 2E, but I want to do the value 2E minus 40. So this is the condition that, this is the case, right? You have small value minus large value. In that case, you do subtraction. Okay? This is just simple binary subtraction. Okay? When you have a 1 into carry, then just you do the simple subtraction into binary subtraction, but your carry flag is now up. Because the small minus large, you need a carry, right? You already did the borrow. You borrowed, so carry flag should be up. Okay? Carry flag is up when you do borrow. Okay? So therefore, there's no subtraction without a borrow. Okay? You always have a borrowing. Let's look at multiplication. What is the problem of multiplication? Multiplication actually is a little bit different. We have a 2 value, and each value is 8-bit. Let's say this is A. Let's say you have a value A, and you have another value in B. And you want to do multiplication. The value in A times the value in B. Each one is 8 bits. Generally, when you do multiplication, what is the output? Output is going to be really big, right? So for example, this is 8-bit, another 8-bit. You multiply these two 8-bit values, then the output becomes 16 bits, right? That's the problem. We don't have 16-bit registers, but the output becomes 16 bits. That's why when you do A times B, the output goes back to both A and B. Okay? We need a 16 bits container for the result. So how you can construct the 16 bits is that you want to put A, B together, B, A together. That becomes 16 bits. Like B becomes high byte, A becomes low byte. So put A, B, and A together makes a 16 bits container. That's the output. You multiply these two, the value goes to this way. So in this case, the value A and B is now updated, right? Originally, you have a value A and B. For example, you want to do 2 times 3. So you have a 2, 3, right? But both value is now updated by the result. Okay? Result goes back to B and A, both of them. So this is the only case that you use B registers. Otherwise, it's not common to use B registers. Okay? But this is a way to use multiplication. there's a division. Division actually is pretty similar. Let's do division. Divide A by B. So A over B. A divided by B. Okay, that's what we need to do, what we want to do. A divide B. When you do division, this is what we are doing, right? A divide B. Or this is what we are doing. When you do this division, you'll have some value here. Okay? And after you do division, you'll have some other things here. This is called the remainder. Okay? And this is called the quotient. So you will have a quotient and the remainder. So here you have a quotient and also you have a remainder. Okay? So the remainder quotient goes to A and remainder, the value goes to B. So in division also, A and B, both registers have a now new value. Okay? A register now has a quotient, this value. B registers now have remainder, that value. Okay? That's the output when you do the A and B, A divided by B. This is the last instruction in arithmetic instruction. There is an instruction called decimal adjust, DA. Right? Look at this example. Probably example is a little bit easier to understand. Here in this line, you put the 2, 3A and put the 2, 9, 29 into R0. And let's do addition. Addition of 23 and 29. Then the value, the output of this addition becomes 4C hex. Okay, 4CH. Okay, A has a 4C. And now you do DA, decimal adjust. When you do that, the value in A now is changed to 52. Why is that? Simply, it actually do plus 6. Okay? A has 4C, so 4C plus 6 becomes 52. So what does that mean? The reason that we are doing this decimal adjust is to make the representation, your hex representation, to BCD representation. Have you heard the BCD representation? What does this mean, BCD? What is BCD? Binary coded decimal? Binary code decimal? Huh? Yeah, I don't, to be honest, I'm not seeing anywhere you use BCD. So I don't know if this is really useful in anywhere. But anyway, what this basically means is you have a binary representation, 0, 1, 0, 1, 0, 1. Okay? And you have hex representation like this, right? This is hex value. We have a decimal representation. And another representation is BCD. And in BCD, how you can represent the value is that you have all the decimal numbers. That becomes the same as decimal, like same. But think about hex. This is a decimal, right? When you think about hex, we have some more numbers. A, B, C, D, E, F. So if you have hex representation, hexadecimal representation, these are all number values, right? These are all alphabets you have. Okay, that's hex, hexadecimal representation. In BCD representation, now how you do it is that A becomes 10, B becomes 11, so F becomes 15. That's BCD. Okay, that's BCD. So here we have a value 4C in A. Okay, A has a 4C. A has a 4C hex. let's change this hexadecimal representation to BCD. Okay, let's change it. This is 4. 4 is okay. So BCD, still 4. C, hex C is 12 in BCD. So let's change this 12. Okay, but this 4 is like a not 4, right? This is 40 basically. This is this is this is 1 and this is 10, right? So this is 4 and this becomes 12. So it's like you're adding 40 plus 12. So it becomes 52. Because this is 12 and this is 40. So plus it's 52. That's a BCD.
Then why we add the 6?
Simply, I mean, this is how we do, right? But if we think about the easy way to convert, then that's plus 6, actually. Think about anyone, any number. 20F. Okay, let's think about this one, 20F. This one becomes 20. F is 15, so it's a 35, right? This one actually the same as plus 6 in hex. I mean, plus 6 is hex, right? So A is, this one is hex representation. This is a BCD representation. So in hex, let's say you do 6. You do plus 6. 4C plus 6 hex. Then it becomes 52. I mean, this one is easy of calculating. Easy calculation of representing or converting hex to the BCD. But anyway, this is the BCD value, 35 or 52. Okay? But this is easy way to do it. Easy way to calculate. So that's the DA instructions. So as I said, I'm not seeing any useful things about this. I don't know where to use this. But anyway, that's available. Let's look at logical instructions. In logical instructions, we have a lot of instructions. For example, and, or, exclusive or, complement. You know all these things, right? Add instruction, or instruction, and things like this. So let's look at example. Here, this is the AND instruction. We have two different values. This one and this one, and let's do AND instruction. Then you know that 1, 0 becomes 0, 1, 1 becomes 1, right? Because it's the AND, logical, bitwise. Okay, bitwise, bit to bit instruction. So this is AND. Similarly, you have OR. When you do OR, 1, 0 becomes 1, 1, 1 becomes 1, 0, 0 becomes 0. Okay, that's OR. So this is OR instruction, AND instruction. This is a exclusive OR, cross OR. Complement. What is complement? 1 becomes 0, 0 becomes 1. That's complement. Okay? So you understand these things. This is pretty easy. So that's the logical instruction. Okay? Here's one thing that you want to remember. Logic instructions do not affect the flags in PSW. What does that mean? Let's say, in this case, let's see. Let's say if you add these two value, let's do addition. Okay, when you do addition, then you have a 1, 1 here in bit position 3. Since you have a 1, 1, you will have a carry from bit position 3 to 4. So the output you have a 1 here. So you have auxiliary carry up. Okay, so whenever you do the arithmetic operation, PSW will be changed. Sometimes carry is up, overflow is up, or auxiliary carry is up. But this kind of logic instruction, PSW is not changed. That's what they mean. So here's a case. Let's say you have all 1. You have all 1 value, right? And now you complement, or maybe you have all 0, then you complement, then suddenly this one becomes 1, but still, the auxiliary carry flag, it's not changed. Okay, this logic instruction does not change anything in PSW. where do you use this kind of logic instruction? There are many ways and many different reasons. Here are the use cases. Look at this one. In this case, right? PSW, you have a carry flag, auxiliary carry flag, and overflow flag, and all those things. Sometimes you want to do AND this one with this. Okay, if you do this, what happened? E7, what is E7? 1110, 0111, right? So if you do AND with this, then what does that mean? Uh, 1110, 0111, and your PSW has some value. This one is a PSW. Okay? And you do AND operation. Okay? The output becomes another 8 bits. What happened here? Same one goes to what? So why do you want to do this? Think about it. Check what? Okay, why is that? Okay, once you do this, right, you have AND operation. So therefore, if some of these bits is 1, then let's say this is 1. In that case, 1, 1, it becomes 1. Right? Let's say some of the bits here is 0. 0, 1 becomes 0. So those bits, right, this is like a filter. Okay? Those bits, you have the same value. You still have the same value. Okay? Because we have a 111, 111. So those bits with 1 will pass exactly the same way. You still have the same value. However, the value in here, right? You have some value here in those 2 bits. This value becomes 0. Why? Let's say you have the value 1 here. Okay? In the original PSW, you have value 1. 1 and 0 becomes 0. And let's say you have 0, then 0, 0 anyway is 0. So when you have a 0 and you do AND, then this becomes 0. So you want to clear this. The other value you want to have same, but only these 2 values you want to clear. Okay? In that case, you use this kind of operation. Okay? Something like this. These 2 are same. These 2 are same instructions. You can use hexadecimal value, or you can use binary value. Either one is fine. Okay? Basically same thing. This is one of the purpose. And let's look at this one. On the second example, what I'm doing is that I'm doing OR PSW 18H. So let's see what happens if you do it. 18 is what? 18H is like 0001, 1000. Okay? And I'm trying to do OR. Then what happened? Same as this one? Let's see. You can actually do it simply. We have a 0001, 1000, and you want to do OR. Right? Okay. So when you do OR, let's say you have some value here. Let's say you have 1. 1, 0, or it becomes it becomes 1, right? Whenever you have 1, it becomes 1. When you have a 0, still 0. Okay? So these bits, it goes down same way. What happened to these 2? These two. Huh? Don't care. Here, let's say you have a 1. 1, 1 becomes 1. Right? And if this is 0, then what? This is 1. Okay? So in this case, here it's always 1. Here it's always 1. I want to set. So this is the condition that you want to clear the middle bits. The middle 2 bits, I want to set it to 0. Okay? In that case, you want to use this kind of instruction. But if you want to set a certain bits, okay, this is just the example of 2 middle bits. If you want to set other bit, you can do it. You can use another value, right? If you want to clear some bits, then you can do it this way. If you want to set a certain bit, or you want to force some bits to high, then you can do it that way. Okay? So this is actually a very popular way. And you know the complement, right? Complement is just flipping the bits. There are other logical instructions, such as clear. Clear means all 0. Make it clear. R means rotate. L means left, its direction. Okay? And C means carry. So RLC means rotate left through carry. RR, rotate to the right direction. RRC, rotate right direction with carry. Okay, let's see what that means. Here. First of all, the clear. Clear, you know that, right? Set all the bits to 0. Like a clear A, the value in A will be 0. Clear C, what is C? C is carry. Okay? When you do this, right? Clear A is a register. So when you do this, the value in the register, the 8 bits, becomes 0. But when you do clear C, C is not a register. C is a flag, just a 1-bit flag. That 1-bit flag becomes 0. Okay? That 1-bit flag. Is there other way to do this? What I want is to clear the carry bit flag. Okay? You can do this way. That's probably the easiest way. But you can do it another way. We know that the carry flag is inside the PSW, right? So you can use this way to clear that bit only. Okay? For example, right? And the PSW, and what value can you have in that case? 7F, right? You have a 7F. Okay, in that case, the lower 7 bits, I want to have the same. I don't want to touch anything for the lower 7 bits. Only the first bit, I want to set it to 0. Because we know that the first bit, MSB, is a carry, right? So you can use a 7F here and use and PSW 7F. Then the carry flag will be clear. Same as this one. Okay, that's another way. Clear byte. This is the address. You go to that address and clear the value in the address. This one, you want to clear the register. And this is an indirect way, right? You go to that particular address using indirect addressing and clear the value. There's an instruction called the swap. This is not that popular. Swap, we have 8 bits, but the left 4-bit, right 4-bit, swap it. Okay, that's a swap. This is not that popular.
Can I use swap between addresses? Can I use swap between addresses?
Between addresses, I think you can. Yeah, you can. But okay. So if you want to do this, right, then you want to copy the address value into A first. Okay, copy the value. Whatever value you want to swap, you first have to copy that value into A, and then call this. In that case, you can do it if you want. Yeah. So let's look at the rotate instructions. Here, this is a rotate. Rotate left. Why do we say rotate? What is rotate? Rotate means rotate like this, right? And left means it's going left side. So when you do rotate, this bit, LSB, least significant bit, this bit goes to there, that bit goes to there, okay? You just move, keep moving to the left. Then this becomes bit 6. Bit 6 becomes bit 7. And where does bit 7 go? That goes all the way back, okay? And the bit 7 goes back to bit 0. So that's a rotate, okay? Like this, for example, you have value F0, that's the original value, and now you run the rotate left. Then, as you see here, this value becomes this, right? The first MSB goes at the end, okay? It becomes 1, and all the other things move to the left by one bit. This is a rotate left. When you have a rotate through carry, like this, I mean, there's RLC also, but this is an example of RRC. So when you have RR, then the exact same. The only difference is that this one moves to right direction. That's RR. Okay, when you have RR, this one goes to there, that one goes to the next, and the last one goes back and becomes first. That's RR. Okay, basically same. And now let's look at RRC. Okay, C means carry. Here's a picture. If you have this one, right? All the bits move to the right, and the last bit goes back goes all the way and becomes the first bit. That's RR. When you have RRC, then now we consider carry. And carry flag, carry bit, you put it here. And this bit basically works as a 9-bit. This one becomes 9 bits, right? Because we have a carry and put it here. And then these 9 bits we have a rotate. So the carry flag goes here. This one move here, that one move here, and the last one goes to carry. Okay? So when you have RR, then you have just rotation within this 8 bits. But we have RRC, then put this carry here and make 9 bits, then rotate. That's RRC. RLC, it's the same. Okay? When you have RLC, put the carry here and rotate with the 9 bits. Okay? That's RLC. Okay, here's the example. Look at the example and see what happens. This picture actually helps you to understand why we need RLC and RRC. Okay. What is actually going back here? You have this kind of shift or rotate. Why do you need this? Do you think of any use case? Any case that you use this one? In fact, this is very useful. For example, this. Let's say what I want is that I want to do multiplication. Okay? Here is an example. Let's say I have value in accumulator. Let's say I have a value 4. Okay? So 4 is 0, 0, 0, 0, 0, 1, 0, 0. So this is my value in A. And what I want to do is that I want to do this. A times 2. Okay, I want to do multiplication. So one way to do is that you want to put 2 here in R0, and you do the multiplication and A R0. Maybe you can do it this way, right? Because what I want to do is A times 2. You can do it this way, right? You have a 2 here, A here, multiplication. Sounds like that's what you need to do. However, this one actually takes a long time. This one is complex. What is the easy way to do? Very easy way to do, very, very easy way, is to use RL. So simply, you want to do this. Then it's the same as times 2, same as A times 2. Why is that? Because when you do this, right, rotate left, now the result becomes 0, 0, 0, 0, 1, 0, 0, 0, because this one now moved to left. Read this one. This one is 8. 8, right? So every time you move to the left, right, move to bit position, move each bit position to the left, every time you do times 2. Let's say I want to do 8 times 4. Then what do you want to do? You want to do, you know, the left. You want to do shifting by 2-bit position. Okay? In that case, the result becomes this one. So it's going to be 16. This is very fast. Very, very fast. Now, then you probably want to ask a question, right? Actually, in this case, it's 4. So now let's say we have a 5. Again, 5 times 2, you want to do shifting. 1, 0, 1, 0, right? Shift, shift, right? That's what you want to do. Now, let's say what I want to do is this. How can you do it? Whenever you do the bit shifting, it's always like a times 2. Okay? Times 2. Because we know that this is a 2 to the 0, 2 to the 1. It's always times 2. Right? How can you do this? Times 3. Any idea how to do it?
double RLA
Double RL?
1.
Yeah, actually that's pretty close. So how can you do it is that this one, 5 times 3, you want to do it this way, right? This one actually is this one. So what does that mean? You want to do RL times A, then it becomes this one. And then, of course, you have to copy this one. You have to make a backup. Like A, let's say I want to do move R0A. So this value now you copy it into R0. Once you do that, then R0 will have the same value. 0, 1, 0, 1, right? Same value. And now you shift A value like this. Then it's the same as 5 times 2. Then you're going to add these two. Then it's the same as times 3, right? This is much, much faster than multiplication. So you can do any multiplication by doing this. Okay? This is very, very effective. So this picture basically shows you that you have the value 3 in A, and if you want to do times 2, then every time you do times 2, you do a bit shifting by left direction. Same way, what if you do right direction? Move to the right. Then it's divide by 2. Okay? Divide by 2. See here, you have a value 18. Then you do a bit shifting to that, then it becomes C, becomes 6. Okay? So every time you move to the right, that's going to be a division by 2. Any question? All right, see you next week.